computer. Okay, so before we get started on the problems, a couple announcements. These are kind of the same announcements from last time, just with some dates changed and then some extra ones. Make sure that you're checking Canvas for resources and announcements, especially announcements. Please check your notification settings. A lot of you are sending me emails asking things that I stated very clearly in announcements. And like, for example, on the syllabus quiz, a lot of people sent me emails about the percentages being graded incorrectly, but I mentioned in class that the percentages had been changed, and I sent out multiple announcements, and I even changed it in the syllabus on Canvas. So I did literally everything I could to let you know about that change. But it seems like just people are not reading the announcements. So please make sure that they are going to your inbox and make sure that you're reading them. It seems like it bears repeating. I see a question about where the notes on Canvas. They're in the announcement I sent out yesterday. It seems to bear repeating. If you miss assignments or extra credit or anything like that because I announced it in an announcement and you didn't read it, I'm not going to give you credit for it. I'm not going to let you go back and do it because you didn't see it before. I send out those announcements and I expect you to check them. Also, you're taking an online course. Everything that we do is online. You need to be checking those things. Quiz 2 opens at 11 a.m. today after class, and it closes Saturday, August 29th at 11:59 p.m. It will appear under module 13 on Top Hat. It's going to cover 1-4 edition, simple Diels-Alder with no serious stereochemical implications. It'll ask you to distinguish between endo and exo, but there's nothing overly complicated about the Diels-Alder problems that are on here. And then I did throw in some module 12 questions. Before next Friday, remember we are not having class on Monday. It's Labor Day. The university is closed, so we're not supposed to have class. Before Friday, finish up module 13. And you also need to begin reading into module 14. Technically, you're supposed to be done with it by Friday, but we are going to go over naming of aromatic compounds and such on Friday. Make sure that if you have any questions that you submit them for the following Monday's class. Module 13 reading questions are actually due just before the next Monday class. Oops, I copied this over and didn't delete it off the first one. Your quiz 3, which is not this week, but next week, will have more complex Diels-Alder problems and naming of aromatic compounds, which is in module 14. And it's going to cover several topics from 2341. Anne and I have talked about this, and it seems like a lot of you do not remember OCHEM 1 at all. A lot of you are really, really struggling with that. Remember that OCHEM 1 is a prereq for this course, which means that you are responsible for that information. If you took Spanish 1 and then you went into Spanish 2, you don't raise your hand and ask the professor to start from the beginning, right? This class is cumulative, just like any other class that is cumulative, right? So you are expected to know the material from the first course, and we are not covering it again in this class. You can come to office hours and ask questions. You can send emails to me and Anne. You can form study groups. All of those things are great options, but Anne will not spend any more time on it in SI. She did spend this last week on it, but now she needs to start working on OCHEM 2 because that's the actual class that you're enrolled in. And this material is going to get really hard really fast. Are there any questions about these announcements before we move on? Okay, great. Okay, so we're going to start with 1-4 edition versus 1-2 edition. I did send this out yesterday and ask you guys to work on the problems. So if we're moving through a little quickly for you, that's part of it. You could work through these on your own. Please just take like a minute to kind of gather your thoughts on this problem. If you didn't start on it yet, that's okay. This shouldn't take too long.
Professor, I don't know if you
Hmm?
chat, but you did mean the 5th that the quiz is due tomorrow on the 5th.
Yes, it's due on Saturday. Mm.
Okay. Just because you still had last in there.
Oh, I'm sorry. Yeah, it's due Saturday the 5th. Oh, sorry about that. Okay, so let's take a look at these problems. So the top one is adding a halogen acid in heat, and the bottom one is adding a halogen acid in lower temperatures. What is that distinguishing? What does the temperature tell us?
It's going to be either 1.4 or 1.2.
Right, so when it's a warmer temperature, something that's heated well above room temperature, we know that it's meant to be a 1,4 addition. If it's at a lower temperature, lower than room temperature, then we know it's meant to be a 1,2 addition. So in this 1,4 addition, let me make sure I can draw. Okay. In this first one, it's a 1,4 addition, and we know that because it's being heated. I only put the 1,2 addition on here just to give you some practice. But we can actually start there if you would like. It doesn't really matter. So remember that, it doesn't really matter how you number these. They could be numbered in either direction. How do we know which alkene to protonate? Let's call this alkene A and alkene B. How do we know which alkene to protonate in the beginning? And I'll go ahead and give us some numbers just so we can talk about the carbons more easily.
Guess the more substituted ones.
Substituted.
Yeah, we want to end up with the most substituted carbocation possible. And we also want to end up with an allylic carbocation, right? So which alkene should we protonate first?
2.
Wait, sorry, the alkenes are labeled A and B.
Oh, A.
Okay. So if we protonate alkene A, which carbon do we put the hydrogen atom on?
On 1.
Right. Why do we put the hydrogen atom on carbon 1?
Because you want the carbocation to be the most substituted.
Right. So by putting the hydrogen on carbon 1, the less substituted carbon, we're following Markovnikov rules. And we also create the more substituted carbocation, and it's allylic. If we protonated carbon B, we would either end up with a more substituted non-allylic carbocation, or we would end up with an allylic but less substituted carbocation. So that's why we end up protonating alkene A. So if we were in the 1,2 edition, as in down here, we would just finish it up by plopping the bromine onto that carbocation. So that kind of knocks that out. In the 1,4 edition, what happens next?
The double bond or the carbocation moves, and so the double bond.
Right, right. We have a resonance form that shows the double bond moving. So your first instinct in words was correct. It's the double bond that's moving. It's those pi electrons. And as a result, the carbocation ends up in a different place. So when we do that, which carbon is the carbocation ending up on?
On carbon 4.
Right, because we took electrons away from carbon 4. So notice we still have a tertiary carbocation and it's still allylic. So we know that we're definitely on the right path here. And then our chloride ion comes in and attacks. And we have our product. Okay, are there any questions?
So we're gonna be able to just know if it's an SN4 because it has heat, right? Compared to an SN2.
You know, a 1,4 edition.
Oh yeah, sorry.
Yeah, that's in the presence of
Yeah,
heat.
yeah. Okay.
Okay. Can everybody make sure that their microphones are muted? There's a whistling in the background. Okay, so this next problem is a Diels-Alder problem. This one is fairly simple. I want to give you about a minute to come up with your product. And keep working. I'm just going to label the carbon atoms so that we can talk about them more easily. Okay, if you don't have your product drawn out yet, that's okay. We're just going to go ahead and talk about the Diels-Alder conventions just to remind you. Excuse me. So remember, you have your diene and you have your dienophile, which is an alkene. The diene has the possibility for 2 substituents on the outside of the alkene. You have your outside substituents and you have your inside substituents. Remember that a ring, such as in our example, is always considered inside. And then your diene can have substituents on it as well. In our major product, we want the electron withdrawing group to be going in the same direction as the outside groups. One of the big things that you have to remember is that the conformation of the dienophile is going to be conserved into the product. So let's say you have an electron withdrawing group here. For your major product, there is kind of a simple formula for drawing it out. The outside substituents, you should draw them pointing down. Your inside substituents, you can draw them pointing up. And then anything that is electron withdrawing, if possible, draw it going down. And then there's always the possibility for an enantiomer, depending on the structure of your dienophile. Now, the tricky thing is if your dienophile is a trans alkene like ours is, you have to see that in your product as well. And if you have multiple electron withdrawing groups and they're trans to each other, you're going to have to draw different products. So I tend not to give you guys examples that are overly complicated, but I want to analyze the one that we're looking at right now. We have, sorry, I'm going to erase these other lines here just so it's not confusing. So we have a cyclic diene, and then we have our dienophile. Which carbons of the diene are going to make bonds to the dienophile?
Carbon 6 and
6
3.
and 3.
Right, so carbons 6 and 3 are where those new bonds are going to be formed from. And which carbons of the dienophile are going to be used?
B and C.
B and C.
Right, B and C. So when you draw out your new structure, you can go ahead and draw your cyclohexane again. Make sure that you switch that diene structure to a single alkene. And then we can make this coming up. So this would be carbons 1 and 2. And then you can draw your other bond to carbons B and C. Sorry, I'm spazzing out. Whoops. I drew something that was perfectly fine and then questioned myself. Okay.
Okay, so sorry, just to clarify, those thick bonds are supposed to be double bonded as well? Like the ones coming?
No, this is a single bond. It's just coming up.
Okay.
So what we have basically is me trying to draw a flat version of what is much better drawn in 3D. Yeah, bizarre how this was faster than this for me. So this is carbons B and C. Now, the kind of tricky thing here is that our outside group was kind of a hydrogen. So if you want to draw those in because it helps you, you can do that. But the electron withdrawing group should be going in the same direction as the hydrogens. Now we have a methyl group and we have a carboxylic acid. Is a methyl group an electron withdrawing group?
No.
No, it's actually electron donating, right? This is our electron withdrawing group. Sorry, the shorthand for this. Can everybody mute,
I'm
please?
in class.
Thank you. Sorry, I cannot mute all when I'm sharing my screen. So we have our electron donating group and our electron withdrawing group. So what we want to do is put the electron withdrawing group going down, and then you can consider your electron donating group. Since our electron donating group is trans to our electron withdrawing group, we're going to draw it up in our product so that these two remain trans to each other. So if we were to color code this, we still have those carbons here. Our new bonds that we made in the Diels-Alder reaction, I'm coloring over in yellow. And then the bonds in the dark blue are the remnants of our diene. And then there's also an enantiomer of this. So this is a thick bond showing you that it's coming out of the page towards you. So we can show the carboxylic acid on the top carbon going down and the methyl group coming up on the bottom carbon. So these two are enantiomers. If you can see it better in the 3D structure, you would put the methyl group up and the carboxylic acid down. Sorry, there's some lag on my tablet right now. And then you could draw the same thing here, down and up. So both of these would form. Are there any questions about Diels-Alder?
I think you cleared a few things up for me.
Okay, good. So the main reason that I wrote this example out is because when you have an electron withdrawing group and an electron donating group on your diene file, you have to make some choices about your major product. If, if your diene file is cis, you don't have to make any choices. If you have an electron donating group and an electron withdrawing group, they both get to go down because they're cis. But when they're trans, you just have to make sure that you put your electron withdrawing group down. Okay, for the major product. So again, this is the endo product. The exo product would have the dashes and wedges of our substituents switched. So you would leave everything else the same, and you would just do some switching here. Okay, let's look at our next problems. So I drew out two Diels-Alder reactions. Notice this one uses two equivalents of the diene. I want you to go ahead and take about a minute apiece. You are going to have to redraw this one because it's currently drawn in the S trans form, but we need it in the S cis conformation. So just do a little bit of redrawing. But I want you to take a second and just spend some time on this. For today's attendance question, let me know when you get it into the S cis conformation. You have two methyl groups, A and B. Let me know if they are on the inside or outside of the diene. Remember, private message. So private message me if the methyl groups A and B end up on the inside or the outside. If they're both in the same direction, you can just say both in or both out. If they're different, let me know that as well.
Dr. B, just to clarify, are you wanting them to draw the enantiomer every time or just put like plus E?
No, they can just write plus enantiomer. If I want you to draw out the enantiomer, I tend to say it.
Okay.
Yeah. I try to be very specific. And if I'm ever not specific enough, please let me know. Okay, spend about 30 more seconds on the first problem and then move on to the second one. Some of y'all are cracking me up with switching your minds multiple times in your private chats to me. Okay, so let's go ahead and start talking about number one. If you feel like you have it, and you're still working on number two, just keep working on number two. So the trick about number one is, again, it was drawn in the S-trans conformation, but we need it to be in the S-cis conformation for our reaction. The easiest thing to do when you are trying to figure out the S-cis version of an S-trans alkene is to leave part of it in the same place and then rotate the other piece. So if you think about rotating this so that the alkene is coming in this way, that does not change the fact that this methyl group is trans to the rest of the molecule. So remember that the conformations of the alkenes themselves will not change. So you should have a trans alkene and a trans alkene. So trans, trans. So that puts both of our methyl groups in which position? Inside or out? Outside, right. I know visualizing that stuff can be really, really challenging. So if you're still, working on that, that's fine. That's why I walked you through my thought process there. So when you're doing a Diels-Alder problem, draw it out in the way that is going to visually push you in the right direction. So everything here was drawn horizontally, which is, kind of obnoxious when you're trying to do a Diels-Alder problem. So I rearranged it and I'm going to visualize, my new bonds being formed. I know I picked yellow, that was dumb. I don't know if you can see that very well. So visualize your new bonds. So this gives me a cyclohexene, right? I know that that's what these 6 carbons are going to make. Now my methyl groups being outside, which direction do I want to point them in? Down or up?
Down.
Down.
Down. Right. And then which direction do I want my nitrile going in?
Up. Wait, no.
Down.
Down.
Down, right. For my major product, the endo product, we want the electron withdrawing substituent to go in the same direction as the outside groups. So my nitrile is going down, and then you would also have an enantiomer. Also, I want to remind you that if you were to flip this molecule over like a pancake, the methyl groups would be up, and the nitrile would be here and up. The key thing is that the outside and the electron withdrawing groups end up pointing in the same direction, right? So if you are taking a quiz on Top Hat and they've drawn the products with the outside substituents pointing up, you're looking for the one where the electron withdrawing group is matching that direction. Right, that's the only reason I'm adding that in. If you're ever just hand drawing the product, following the convention of putting everything down is good. Okay, our next one is a little trickier. When you have a product like this that's going to form, you know, a product with 3 rings, right? Because, oops, I don't know how I keep doing that. You might want to kind of draw out like a rough sketch before you worry about any of the stereochemistry. So we know that we're going to end up with 3 rings. And our ketones are going to be unaffected. They're in our dienophile. Notice, you know, this cannot be our diene because this is not a conjugated diene system. There is conjugation like going through that way if you want, but that's not going to create a diene for a Diels-Alder reaction. This is a dienophile. And then we're going to have some methyl substituents. You kind of have to decide, do you want your other methyl here or here? It doesn't matter, they're going to lead to 2 different products, so you're probably going to want to draw both. And then our alkene is going to be there just like you would, you know, rearrange your alkene and go here in your product, right? So draw out the main frame of your product before you do anything else. That'll just make your life easier. And then you can draw this going down if you want. It doesn't really matter. Does anybody know why it doesn't matter if you draw this down or not? Remember that the
Resonance? There's a lot of
no
resonance. No?
no although resonance is the answer in organic chemistry about 50% of the time, so that was a really good try. So the reason it doesn't matter is that both of these substituents are hydrogens. So it doesn't really matter if you draw it up or down because there's no substituent to compare to. So remember, the endo product has the electron withdrawing group going in the same direction as the outside group, but there is no outside group. So it doesn't really matter how you draw it. So you can draw it flat, and then you're also going to have the product where the methyl groups are going in opposite directions.
Can you say that again? The electron withdrawing group goes in the same direction as
the outside substituents.
Okay. Thank
And
you.
that's for carbons 1 and 4. So this methyl group does not matter. So anyway, we're gonna end up with these 2 products, and the directionality of these bonds in the middle doesn't matter because we don't really have an outside substituent. Are there any questions about this page?
And that's just all you're doing with the bottom one?
Yeah, that's all we're doing with the bottom one. This ends up giving you the products. If there had been some substituents on here, we would have to make sure that we indicated some stereochemistry, but there aren't, so we don't have to worry about it.
What would it look like? I'm sorry, this is just, I feel this is something that would catch me up if it showed up, but what would it look like if there was some extra stuff to worry about, some extra constituents?
Like if there had been a substituent, you would want to, put it down, and then you would want to show these bonds going down as well. But then there'd probably be some kind of tricky stuff. The reason that I wouldn't do this to you guys with a situation that was going to form 3 rings is because this could end up. So there would be a lot of complications there. I wouldn't do that to you guys.
So, quick question: how do you end up getting like the trans version of the product?
Do you mean like the one on the right versus the one on the left?
Yeah.
Oh, it's just which direction this is going when it reacts with the dienophile.
Okay.
Yeah, so it's just how did you, imagine your diene?
Okay, so it could like essentially go at it both ways. So both are like equally.
Right, so both of these would form, and they're not enantiomers of each other. They are just different molecules. You could kind of consider them diastereomers.
Would one be major over the other?
Probably not, because these are so far apart that I don't think they would have a steric effect on each other. Okay, let's move on to the next slide because it's 10:39. I do have to leave class on time today. My in-laws are coming through here from 11 to 1 o'clock, and we haven't seen them since Christmas, so I have to go eat lunch and everything. Okay, so for this one, identify the diene and the dienophile used in the synthesis of each of the following. I'm just going to work through one of these with you guys and have you spend the rest of your time on this at home. I'm sorry, I should have drawn these bonds going down. So when you're doing this type of problem, you just have to know which bonds were formed in the reaction, right? So how do you figure that out? What piece is always the same in a Diels-Alder product?
I know the dienophile is usually very electronegative. Is that the right word?
Yes, it's going to have high electron density because you'll have electron donating groups. But what piece of the structure is consistent through every Diels-Alder product?
A hexene.
Right, we have the cyclohexene structure. So this is here. And the alkene always ends up in the same spot, right? It's going to be in between the carbons that used to be part of the diene. So the bonds that are made are always the ones that are essentially opposite the side of the alkene. So the first part of this is always just identifying which bonds were made. I'm going to pick a different color so we can see this more easily. So these bonds were made, right? The ones that are opposite the alkene. From there, you just kind of have to imagine taking, some scissors or something and cutting right through that. And then you have to spit out the appropriate diene and dienophile. So if we broke those bonds, we would have a 1, 2, 3, 4, oh, sorry, 1, 2, 3, 4, 5 carbon piece. All right, so I'm just drawing out the same carbon structure again. And the alkene is currently here, but since we know what Diels-Alder does, we know that the diene must have looked like this. And then the other part of the structure would be the dienophile, right? And we know that that should have an alkene. So that's all you have to do is just look at your product and visualize breaking it apart.
So for the product, could you leave the hydrogens off? Like, are those really necessary?
No, you don't have to draw them because like they're implied, right? Any carbon atom that is not drawn out with the letter C, the rest of the hydrogens are just implied.
If this was the question on the other way around, would we have to draw our hydrogens? Was that just the question she just asked?
Yeah, that's kind of what I was going to ask.
Okay. No, you wouldn't necessarily have to draw these hydrogens as long as you indicated that these bonds were going down. The reason that these were drawn this way, I actually pulled this structure from the textbook, and they did not draw the down stereochemistry on these bonds. But by drawing these up, it implies the down stereochemistry here.
Okay.
So yeah, that's why they drew them, is because it's an easier way to show that than to try to draw this bond dashed.
Down.
Yeah.
Okay. Thank you.
Yeah, no, you would not have to draw them as long as you showed the appropriate stereochemistry somehow. I see a question about the last problem. I will go back and explain that in a PowerPoint. I'll draw the structure out. I'll draw the mechanism out a little better. Okay. So go ahead and do the rest of these on your own time. I want to move on to the next problem because we only have 6 more minutes left of class today. And I'll finish all of these another time. Oh, look, I accidentally repeated this question. Oh, I took both of these from a previous quiz. Sorry about that. Skip that slide. Okay, this one is a synthesis. And I really like this problem. It's a little tricky. What you have to do is recognize that since there is a cyclohexene here, that this must have been made through Diels-Alder. So what this is telling you in this problem structure is that you have to use this compound somehow. You have to turn it into a piece that could be used for Diels-Alder. And then you can use any other carbon pieces that you might need. So seeing that this has a ketone and has 1, 2, 3, 4 carbons total, which piece of the molecule do you think this is going to make? Is it going to make our diene or our dienophile?
A dienophile?
Yeah, we could make our dienophile really, really easily from this. So if you break this apart mentally using the thing that we just did, right? We want to break these bonds. So we know that these 4 carbons must come from our diene. These 4 carbons come from our dienophile. We can identify the structure of our diene and our dienophile. And now both of these can actually be made from the starting material, but I'm not going to require you to make this from the starting material right now if you don't want to. That would be a good practice problem to do on your own. How could we take this reagent and turn it into our dienophile?
Introducing the Mg. So take away the bromine.
Yeah, how would we do that? What reagent could we use? Oh, you guys did this problem in SI?
A very similar one from actually my final last year.
Nice. All right, we want to eliminate the hydrogen. I used the word eliminate on purpose, right? Because we want to make an alkene. So this is an elimination reaction. What could we use to pull off the hydrogen and kick out the bromine?
Mg and ether.
H2SO4.
No, we don't want to use acid or magnesium and ether. Magnesium would turn it into a Grignard reagent. I see in the chat from Isaiah, T-butoxide, potassium T-butoxide. That's perfect. So if we use a bulky base, it's not going to be a good nucleophile. It would do a good job of eliminating. What other reagent or condition could we add to make sure that it definitely does an elimination?
Heat.
Yeah, we could also add heat. Sorry, I don't know why it's only writing half of my words sometimes. Yeah, so we could add heat and guarantee the elimination. So something that I would like you guys to work on is how could you turn this reagent into this? It's actually not that hard. We just don't have a lot of time. So you can work on that on your own, and I will go through this slideshow possibly today. I have several meetings today after lunch, but at some point I will give you the answers through a video. Okay, this is another problem. This is actually from an old quiz that I've given before. And so I put it on here because it covers several really important things. You have some OChem 1 and you have some OChem 2. Notice we're creating a ketone. Oops, sorry. There's some oxidizing reagents here. We have halogens and magnesium. So this is a pretty decent mix of OChem 1 and 2. And then on the next slide, you have a lot of the same situations. We have some reducing agents here. And then somehow we're going to end up with an aldehyde. We have a Grignard. We have an epoxide. That's a little OChem 2 from the Grignard, but the epoxide ring opening, that's from OChem 1, right? This is going to be an SN2 reaction. You have to remember the rules of SN2 essentially. And then some OChem 2 reagents. So this is a pretty fun mix, I think. I would work on these problems before you take your quiz. Not all of these things appear on your quiz, but if you can work through these problems, the quiz will be no problem at all. So practice your Diels-Alder, practice your 1,4 addition, and make sure that you understand how to get the most stable carbocation, and then practice all of these reactions. Next week's quiz number 3, is going to have a lot of OChem 1 on it, just because that seems to be the only way that I can make you guys be responsible for that material. So I'm going to hold you accountable for OChem 1 next week. Are there any questions? Any questions? Okay, well, I'm gonna let you guys go. Thanks for a fun class. If you do have any questions, send me an email. I'll be back to work around, actually I have a meeting at 1 o'clock and at 2 o'clock, but I'll be checking probably around 3. That's when I'll be back to it.
Thank you.
Thank
you guys. This is the most fun part for me. So
I'm gonna, oh, sorry. I'm gonna email you the study sheet I told you about, like with the OChem 1 stuff.
Okay.
Like today. I'm just finishing up and then I'll email it to you later. I didn't know if you wanted me to post it to Canvas or if you just wanted to look over it.
I can take a look over it just to make sure that we cover it all. If you want to go ahead and post it to Canvas just so they have it, that's fine. And if we want to add to it, we can. I really doubt there are mistakes on there. So I trust
No,
you.
yeah. Okay, thank you.
Yeah. All right. Talk to you guys next Friday in person.